indeed, actually, randomized algorithms is a fascinating branch of algorithms. A lot of very interesting algorithms are actually randomized. And luckily, we have one of the best teachers who teach randomized algorithms in this building, Surendra Baswana. So I would really recommend you to take a course if he teaches randomized algorithms. It's a fascinating subject. You have a fascinating teacher. It can't get better than that. Okay. But anyway, getting back to randomized algorithms, I will say now, I told you, right? What was the idea? Now we say that an algorithm has two inputs. This was our original input and this was random string. And I said that for most of the R's you should give the correct answer. This is the more studied model of randomized algorithms, but actually there are two ways to relax the constraint. Okay. Again, randomized algorithm, what are we doing? We are allowing this random string and then we are looking at how the algorithm performs. Now, in terms of correctness, I need not relax the correctness, I can relax the cost. I can say that my algorithm should always answer correctly. But then the cost of the algorithm on X will be this, and then you will maximize over all X's. Okay. So first, very important, in whatever algorithms you analyze, the cost is worst case cost over all the inputs, right? What is the cost of the algorithm? You say, what is the worst input for this algorithm? That is the cost I am going to take. So you maximize over X. Now, ideally, if this was the input, you want to maximize over X comma R. Okay, but I am relaxing cost. I am saying that my cost is expected over R, the cost taken by the algorithm. Okay, and just because we never have fun in this class, this is called the Las Vegas model of randomized algorithms. Okay, and in no way I promote gambling, even though I teach randomization. And the second way is to actually relax the cost, relax the correctness, which you have already seen. In this case, my cost will be max X over R, the way you would think of it, but correctness would be for all X is correct, the probability that my algorithm is correct over R is high. How high? It actually doesn't matter much, but generally we choose this number 2 by 3. So you are saying that on 2 by 3, if you are picking R's uniformly at random, you are saying on 2/3 of the R's, my algorithm should answer correctly. Questions? So these are two ways in which I can define. I will answer Suyesh's question, but this is called Monte Carlo. Yes, Suyesh. On some R's, it can take very long time.
You are not putting a bound on how long it should take.
But you should always give the correct answer. Okay, so clearly estimating the value of pi, we had relaxed the correctness, right? Questions about these two different models? So again, the fundamental fact in randomized algorithm is that you have a random string as an input. Now, if you do not relax cost or correctness, you get your deterministic algorithm. So there are two ways you can say, oh, I will only take expected cost over R. Or you can say that you should be correct on most of the R's. Very, very important point, even though I tell this 100 times, people confuse, is that this expectation and this probability is not over X. It is only over R, right? Probability and expectation are over R and not X. Okay? Your algorithm should run on every input, not on most of the inputs. For all the inputs, most of the R's. Okay? Great. And relaxed cost. I will give an example of a randomized algorithm where there will be a relaxed cost. But again, in the normal computer science world, when you talk about cost, the cost is the worst case cost. Whatever be my input, if one input takes only 1 minute, but if one input takes 1000 minutes, then I will say cost of my algorithm is 1000 minutes. If you take this definition, and since your input is x comma r, your cost would ideally be max x comma r, cost of running algorithm on x comma r. But this is what I am relaxing. Now instead of worst case cost, I am saying that my algorithm's cost is expected over r cost axr. So if my algorithm was running with half probability in 1 second and half probability in 100 seconds, then my cost of the algorithm is not 100. It is 50.5. Right? So this way, and this is what I will compare with my deterministic cost and say whether there is an improvement or not. Okay? And to make our life simple, any Las Vegas algorithm can be converted into a Monte Carlo algorithm with just a constant factor loss in cost. And we don't care about constant. We are computer scientists. This can be observed inside theta. So if my algorithm was running in 2n square, now it will run in 20n square. Who cares? I will give you an idea of this as an exercise. You can try to do it. The idea is very simple. Your expected cost is small. On some inputs, your cost could be, or on some R's, your cost could be very, very high. What you will do is, you will stop your computation after 10 times the expected value. And now the probability that your algorithm runs more than 10 times the expected cost is very, why? What is it called? Markov inequality. Your expected value is x, is e. What is the probability that you go up to 10e? More than 10e, 1 by 10. This is Markov's inequality, right? So then there is a very, very small that we go above 10e. I will assume I am answering wrongly in that case. There is an error probability allowed in Monte Carlo, right? So I will absorb that probability. That's all. Okay? Sorry? You can't answer wrong. So that by cutting it at 10e, I will have a small error probability, and that error probability will be in the relaxed correctness thing. So then Las Vegas can be converted into Monte Carlo. We won't be running it till it gives me the correct answer. We will running it till 10 times the expectation or 20 times the expectation, depending upon how small a probability of error you want. Okay. And once again, don't fret over this 2 by 3. This 2 by 3 can be made at 3 by 4. It can be made 99 by 100 just by constant many increase in your cost. Again, the idea is to repeat the algorithm. If time permits, I will explain it. Otherwise, it is there in notes. So important thing is to not worry about this constant 2 by 3. Any constant more than half, we are happy. Great. That means we will mostly be talking about Monte Carlo algorithms. And that means we will be comparing our algorithms with Monte Carlo algorithms. R means quantum algorithms with Monte Carlo randomized algorithm. Questions? You're fine? How many people have taken a course in randomized algorithms? One. Okay. How many randomized algorithms have you seen today? I need to wake you up from time to time. How many randomized algorithms have you seen? I will answer your question, but first answer mine. I asked the question first.
One was finding the value of pi with the dart method, but then computationally we are calculating
That's just one algorithm. Have you seen any other algorithm? Balanced versus Deutsch-Jozsa problem, right? Was it a Monte Carlo algorithm or a Las Vegas algorithm? It was a Monte Carlo algorithm again.
and even this one was Monte Carlo, right?
The Dart one was also Monte Carlo. Correct? So we have already seen two kind of randomized algorithms. And if you look at Deutsch algorithm, and actually most of the algorithms we will see in the class, the answer is a Boolean answer, right? And I've already made your life complicated. I said there are two models, Las Vegas and Monte Carlo. In my defense, I've simplified your life by saying we'll only worry about Monte Carlo, correct? So let me make your life complicated once more. Okay, now we will mostly be interested in this kind of problems where we have a Boolean answer. We are computing a value of function, or more generally, you have an x, you want to calculate whether it's in some language or not. If people are not comfortable with this language 0, 1 star, I can stick to functions. What are regular languages? Model. What do you mean by model? Finite automata. Okay, I will stick with this f0, 1 to the nth 0, 1. Okay, so then we have basically, the point is we have a Boolean answer, right? Then what does this relaxed correctness means? If f of x is equal to 1, then probability over R AXR is equal to 1 is greater than 2 by 3. Correct? Correct? Agreed? Now, this is what we wanted. We have seen a problem in Deutsch-Jozsa, which was a problem with Boolean output. Did this happen in that case? So, again, you can take it as 1 minus delta. So, that's not what I'm talking about. Delta changing is not the important thing. But did this happen there or something else happened there? So let's say this was the case of balanced, this was the case of constant. Remember Deutsch's problem, right? you are given a string of length n, either all n values are the same Boolean values or half of them are 0, half of them are 1. You want to distinguish between these cases. Balanced is the one when half of them were 0, half of them were 1. Constant was the case when they were all zeros. No, okay, you are right. So there is one way where you say, oh, if AXR is equal to 1, then it could be both balanced or constant. But if I answer balanced, then it has to be balanced, right? But other way to put it is that if the string was balanced, then I could answer both balanced or constant. But the probability of answering constant was very, very small. But indeed, if my string was constant, then I will always answer constant. So this was actually equal to 1 in Deutsch-Jozsa case. Right? So you remember Deutsch-Jozsa randomized algorithm for Deutsch-Jozsa problem? You pick some random places, and if all of them are the same, we say our function is constant. If all of them are not same, we say the thing is balanced. Now, if I give you a string which is balanced, with high probability I will see both 0 and 1. But then there is a small probability that I see all zeros, all ones. This 1 by 2 to the power 5, 1 by 2 to the power 64. So then the probability that I indeed I answer balanced when the balanced string is given is more than 1 minus 1 by 2 to the power 5 or 1 minus 1 by 2 to the power 30 or 1 minus 1 by 2 to the power 64. What happens if the string was constant? I pick 5 places, I will always see either all of them 0 or all of them 1. I will never see 0 and 1 together, right? That means I am always going to answer constant. I am always going to answer correctly, right? So this probability is not just greater than 1 minus delta, it's actually equal to 1 in this case. Okay? And I want to emphasize this because people study randomized algorithms in these two different settings. What happened there is called one-sided error model. Okay? And this is what you would guess if fx equal to 1, then probability over r is greater than 1 minus delta. You can change these two also, right? You can say that when fx equal to 1, this probability is 1, and when fx equal to 0 is 1 minus delta. The usual, more general case is called bounded error model, which is what I had written there. Or let me just put it this way. Probability that I get R, so this is for both 0, 1, my probability is greater than 1 minus delta. Okay? The small reason, one of the reason why I am telling you these two models again, in quantum, mostly will be worried about bounded error model, right? Monte Carlo algorithms, bounded error model. Okay? But sometimes when we get one-sided error models, life is easier. Okay? Let me explain to you why. I said that this constant really doesn't, or let's say this constant really doesn't matter. What does it mean? What constant can I choose? I can choose 2 by 3. I can choose 3 by 4. So delta equal to 1 by 3, delta equal to 1 by 4, delta equal to 1 by 100. Correct? What about delta equal to half? Exactly, right? So delta equal to half does not make sense because I have a trivial algorithm to solve any problem in the world with delta equal to half. I will not worry about the problem. I will toss a coin. If head, I will answer 1. If tail, I will answer 0. I will succeed with half the probability. You see this? Right? So delta equal to half is not something. So what we want is that delta should be strictly less than half. This is, we are talking about randomized algorithms with Boolean answers. Doesn't matter. Sure. Again, you always confuse. So good, right? The probability is over R, not X. See, after so many times, still this confusion will be there. Not just him. You will also have this confusion, and that's why I'm clarifying it again and again. Probability is only over R, not over X, right? So then either fx is 0 or 1. If fx is 0, I will reach tail half the times, I will be correct with half the probability. So then when I say the probability is 1 minus delta, delta is less than half. Okay, any delta less than half is equivalent in the sense that constant amount of repetition will go from delta to delta prime. Okay, but again, this does not mean you can take half minus 1 by n. Delta has to be a constant. It should not depend on it. Otherwise, number of repetitions will depend on that probability. Okay, this was a small thing, but again, we won't get into that many details in most of the things. But now, same thing here. What can I say about delta? Delta less than half?
Because you know the not of the actual answer.
So what does it mean? Then what kind of deltas am I allowed? Notice, now your flipping the coin algorithm is not working. Because flipping the algorithm coin gives wrong answer on both sides. Right? The flipping the coin algorithm, the dumb algorithm where you don't even look at the input, gives you wrong answer on both the sides. Sorry?
Exactly, it's the wrong answer. Know if you know it's always the wrong answer, and you know what the right answer is. So if it always gives 0 when it should be 1 and always gives 1 it should be 0, it's still a perfect answer.
No, I'm not saying that. I'm saying, again, you keep going on different x's. Your x is fixed. Let's say fx equal to 1. If I toss a coin, half the time it will give me 1, half the time it will give me 0. There is an error probability. Now fx equal to 0. Again, half the time it will give me the correct answer, half the time it will give me the incorrect answer. So there is error on both the sides. So clearly it is not bounded error. I want one-sided error, right? Are you converting one-sided error into deterministic algorithm? That you can't. You can think about it. You can't take one-sided error algorithm to create a deterministic algorithm. Okay? But now, what can we say about delta? Yes, exactly. So here, even if I succeed in this fx equal to 1 with 0.01 probability, you have done your job. Okay? So when you are making randomized or quantum algorithms, in the case of bounded error model, as soon as you get the probability higher than half, you are happy. But, and since you have taken a course in randomized algorithm, you might have seen in the classical world, most of the randomized algorithms are actually one-sided, like Deutsch-Jotza. And in that case, On the other side, even if I have a small non-trivial probability of being correct, my randomized algorithm has succeeded. I'm done. Okay, so you will be developing randomized algorithms, you will be developing quantum algorithms in these two models. What you have to remember is, if the error is on both sides, then you want probability to be strictly higher than half. If the error is on just one side, that error side, we get it higher than any constant, any small constant, 0.00001, we are okay. We have created a non-trivial randomized algorithm. Sounds good? So this actually comes out, this is basically a repetition that this any delta less than 1, delta and delta prime are related by constant many repetitions. Any delta and delta prime less than half are related by constant many repetitions. Actually, the calculation is simpler here. This follows from Chernoff bound. This you by simple elementary probability you can try. If you are stuck, there are notes to help you out. Questions? Right. Good, good. So let me just repetition. I will just mention this repetition point again. Remember, we are in the Boolean world. That means our answers are Boolean, right? So I have an algorithm A prime which succeeds or which fails. So this is the let's say bounded error one. Fails with probability, let's say 1/3. Okay. Cost is, let's say, root n. Which one should you pick? Which algorithm is better? Sorry. Yeah, this is correct. Yes. Huh. No, that's the point I'm trying to make. Everyone is confused. Which one should I choose? Or for someone it is clear? Except the people who have taken randomized algorithms course. Huh? A is actually indeed better. The reason is I can repeat A constant many number of times. So that means my cost will become this, and this error probability will become 1/10,000. So if I had said the algorithm A has cost C times order root n and error probability 1/10,000, then clearly A is better. I'm saying you can convert A into that kind of algorithm. Just by repeating A multiple times intelligently, you can create, actually it is not even intelligent. You repeat A multiple times, take the majority. Okay, that will give you a correct answer with probability 1/10,000. C will depend on, but it's a constant, doesn't depend on it. So now you clearly see that A is better than A prime. And this is saying that if I have this factor, I really don't care what this factor is if it is less than half. Okay. One-sided error model. Okay. Which one is better? Still, A is better. Okay, because you can repeat A multiple times. Look at A prime, okay, which succeeds, which fails with probability this much, and still the cost is order root n. How many people are surprised with this? How many people can prove this? Yes, all of you should be able to prove this. This is the exact same calculation we did for Deutsch-Jotza. Remember, Deutsch-Jotza could have just this simple algorithm. You query it 2 times. If you see 0 and 1 both, you say balanced, otherwise you say constant. But you said, let me not query it 2 times, let me query it 10 times or 20 times. You repeated it and the probability went down, right? Actually, it didn't matter, it was half. So this transformation is actually elementary probability. You don't need Chernoff bound, you don't need anything advanced. So anyone who has basic probability, high school probability can make these calculations. You won't take majority this time. It's a one-sided error. So that's the important thing to realize. So let me give this as a homework. If this is not something which you can prove it. It is a very, very good exercise in probability. You have an algorithm which fails with probability 0.999. You want to convert it into an algorithm which succeeds with probability 0.99999. You can do it with only constant many repetitions. Constant means it does not depend on root n. It could be 10 million, it could be 1 million, it could be 10 billion, I don't care. It does not depend on n. But that constant is really not that bad. You can try. Okay? You can. Huh. So if how did I define one-sided? Huh. My input is fx equal to 1 and 0.9999 times 0.9999 fraction of r, I am answering 0. Exactly. That is the advantage of this. Is the reason why I introduced one-sided error model. Good. So many of you are in the same boat, and that's why you should make this conversion. Okay. Once again, what is the conversion? You have an algorithm A which fails with probability 0.9999. You want to convert it into an algorithm A prime which fails with probability only 0.00001 time with constant repetitions of A. And this definitely requires the fact that you have a one-sided error model. Okay, so there is the algorithm which has a failure probability of 0.999 in the one-sided model is still a non-trivial algorithm. You have one, if you can create a one-sided error algorithm which has failure probability 0.99999. That's what I'm trying to emphasize. Okay, and if you are confused about A and A prime, there is no role of algorithm. You have a coin, think of it gives the correct answer, it heads with some probability, tails with some probability. What will you do? You can try that also. Same calculations. Okay. This one-sided error model is really, really strong. And in many cases, you will get into that. And then I will say, oh, my failure probability is like 0.78 and I'm happy. That time you should not be. Whoa, what is wrong with you? We know 0.78 failure probability is good for us if it is a one-sided error model. Success probability. You keep going from different axes. What do you mean? Huh. Correct. Okay, you for which x? For which x? For which x will you flip? You don't know. If you flip for all x, then for other thing you will get the wrong answer. And when I said that my failure probability is 0.78, it does not mean that for every x my failure probability is 0.78. It might be 0.25 for something. I'm not saying that my failure probability is exactly 0.78 for all the x's. If that was the case, yes, you could flip.
Would apply in the bounded error model. If we have delta greater than 1/2 in some bounded error model.
Yes. If you knew that that probability was exactly equal, there is a greater than equal to sign here. For some x's you might be completely correct. So you don't know, you are saying flipping, but for what x are you flipping? For some where you are flipping, you got correctly answer. From 1/3 to 2/3, you got to 2/3, 1/3. But then in somewhere you were getting the correct answer always. Now you are always getting the wrong answer. So this is why I keep emphasizing this probability is over R for all x. Okay, and many a times you will forget that there is this for all x hanging out, and you will create algorithms where your x is either fixed or you're taking probability over x, and then you will be wrong. Okay, and again, take 5 minutes and think about it. You will find out the flaw in your reasoning. Okay, otherwise I'm always there. I'm not running away, so I can clarify this. But no, this stupid trick of I don't want to say stupid. I mean trivial trick of flipping from 1 to 0 is not going to happen. Okay, thank you.